Hello, we're going to talk about vector algebra in 2 dimensions. So, we're going to look at a few properties here. Given two vectors in the plane, and we're going to call vector u. We're going to identify its components as u sub 1 and u sub 2, and vector v sub 1 and v sub 2, and the real number lambda. So this is going to be a real number, not going to be some type of vector, right? The sum of two vectors, u and v, is defined by u plus v. So we can take their in column of vectors, u with components u sub 1, u sub 2, plus the column vector v sub 1, v sub 2, and then you can write them as one vector this way, so we can add them together. Then the product of a scalar, often in vector we call that a scalar, so that real number lambda as a scalar, and meaning we can scale it to something, and a vector u is defined by, if we take that scalar times u, then we can take its components and scale it by that lambda u sub 1, lambda u sub 2. And then we have the zero vector, the null the null vector, right? They usually use this notation. It's a capital, or I should say a bold type 0, meaning some type of vector, and that's just going to be 0, 0. So the linear combination, or not the linear combination, the column vector 0, 0. Sounds kind of weird. It's just one point, but we can represent a single point, the null vector, as just a vector 0, 0. And then the opposite vector of u, if we have u sub 1, u sub 2 minus u, is negative components, negative u sub 1, negative u sub 2. It should make sense. If it's going in the opposite direction, it's just going to go, instead of u sub 1 units, it's going to go the opposite direction of that u sub 1, and the same thing for u sub 2. So we're going to use this to, these properties here, to solve a couple of problems. First one we're going to look at here is example 8. It says let a equal the vector 1, 3 and b be 2, 2. Find in component form a plus b. So a plus b, right? Well, that would be 1, 3 plus 2, 2. And using the property we saw on the previous page, we can write that as 1 plus 2 over 3 plus 2. And then that's going to be the 3, 5, right? And then they want us to draw a diagram to show what this looks like. So the way we can do that is just like this. And so if I go, the first vector would have been 1, 3, so I can go over 1, then up 3, just like that, and then that would be that vector right there, and that's a. Good. And then from there I can use the vector 2, 2, so that'd go from this point, I can go over 2 and then up 2 right here, and that would be right about there, so that would be b. And then we can see that this vector here would connect them right here, and that would be a plus b, and we can see how that works, right? That would be over 3 and then up 5, 3 and then 5. You can see how that works geometrically as well, and see how all this fits together with the algebra and with the geometry. So let's go ahead, look at the next one. Next one, it says let a equal 1, 2. Find 2 times a, 3 times a, negative a, and a negative 4a. So if I have, let's go ahead, if this is a, and if I wanted to find the vector 2a, right, what would that be equal to? That would be equal to 2 times 1, 2, right? Which is the vector. We can use the scalar multiple that we saw on the first page, and that's 2, 4, right? So a little sloppy there, but that's 2, 4. Good. So next one is 3a. So 3a, well, that's the same as 3 times 1, 2, which is going to be 3, 6, right? So that's that column vector. And then the next one is going to be negative a, the opposite vector, right? So that would just take this 1, 2 and make both of these negative 1, negative 2. Good. And then the last one, they want us to do negative 4a, right? Well, that would be negative 4, right? I got a negative 4, and then it's 1, 2, right? So that would be negative 4, negative 8. Then they want us to draw a diagram to represent all of these. So I'm going to go ahead and try to draw a diagram to represent all of these. Let's see if we can see what this looks like. So let's just do this here, and then maybe we can see what's going on. And so for the first what was a equal to? A was equal to the vector 1, 2, right? So that's what that was equal to. So if I go 1 and then up 2, that vector right there represents A, right? Good. And then if I wanted to do 3A, first one is 2A, right? That should be 2, 4. I'll start right here so you can see what it is. A vector can be moved around anywhere you want, but just so you can see them, I don't want to do it right on top of it. I'd go over 1, 2, then go up 4, right? So you can see that vector right there. It's roughly, that's 2A, right? Good. And then we can do 3A, the same thing. I'll start it right here. So 1, 2, 3, and then up 6. This is 4, 5, 6. So it's like right here. And you can see that's just scaling right here. So this is 3A. And then negative A, right, would be the same vector but going the opposite direction. So I could just go over 1 and then up 2 right here, but I would just draw my vector that way. So that's negative A, right? Good. And then a negative 4A, right, is, well, I can go over 1, 2, 3, 4 if I start right here, but then I got to go up 8. And this is 6, this is 7, this is 8. So that's like right about here. But likewise, instead of going that direction, right, I'm going to make sure I go that direction right there. And that's a negative 4A. So we were able to show each of these vectors that they asked us to do. Negative 2A is right here. Negative 3A is right here. Negative A I wrote right here. And then negative 4A I wrote right here. But this one is just going this direction. And there you go. Thanks, guys.